Alright, so during class on Wednesday, we went through the last of the material for the independent samples t-test and switched over to start going through this worksheet that goes through an example of hypothesis testing with the independent samples t-test. Now, we had gotten up to the point of trying to calculate what the comparison distribution standard error would be, which with this test ends up being a bit more involved because of the fact that we have two different samples with two different amounts of variability, and we need to figure out some way to come up with a compromise that we can use for this estimation for the population. So we went through and actually did the calculations for the first group, which again we had to get the mean first in order to get the deviations from the mean, and then of course the squared deviations from the mean here. So the mean 12.55. Once we calculated the square deviations from the mean, that's what is entered up here, and then divide by n minus 1, which is degrees of freedom for that group. We then, and this is where we are picking up, move on to the second group, which we calculate the mean for, which is 9.5, and we take that mean, subtract it from each individual score down here, and then take those values and square them. So we get the squared deviations from the mean. We enter these up here because we have to add those up and divide by n minus 1, which again, sample size is 6, so 6 minus 1 gives us 5. So the variance for that second group is 0.82. Alright, so moving along in our attempt to pool these variances. So a few things that we need, because first off, we need to have some way to determine how much of a group is going to contribute to that variance estimate. So we've got two variances we've calculated, one for group 1, one for group 2. Now we have to figure out, okay, how much of each will go into the pool. So the way that we do this is that we assign a weight to the variance for each of the groups. And the weight is determined by the degrees of freedom for group 1, which n minus 1 gives us 6 minus 1 or 5. And then we have degrees of freedom that go along with the second group, which again is n minus 1 or 6 minus 1 gives us 5. And as far as what sort of big picture number here that we're dealing with, the degrees of freedom total, which is degrees of freedom for the first group plus degrees of freedom for the second group. So 5 plus 5 gives us 10. Alright, so to calculate the pooled variance, we take the degrees of freedom for the first group divided by the total degrees of freedom. So that's essentially weighting the amount that the variance for the first group is going to contribute to this estimate. Second group, we will put the degrees of freedom for that group divided by degrees of freedom total and multiply it by its variance. So essentially we'll have 5 divided by 10, multiply that by the 0.77, which is what the variance was that we calculated for the first group, and then for the second group we'll have degrees of freedom of 5 for that group divided by total, which is 10. Multiply that by the variance that we got for that group. So essentially this, once you crunch the numbers, basically we are going to cut 0.77 in half and cut 0.82 in half, gives us 0.385 plus 0.41, and I went ahead and rounded this so that we're only dealing with 2 decimal places. Gives us a pooled variance of 0.80. Now, we need to convert that pooled variance, which is squared, the squared deviation of the standard error. So, yeah, mouthful, a little confusing, but essentially we have the pooled variance here, and we are trying to ultimately get to a standard error estimate for our comparison distribution. So in terms of the contribution from the first group, so here you'll notice that we have S sub m, which is for standard error, but it's designated with this superscript 2, which indicates that it's squared, and specifically for the first group, which is why there's this X here. So we take our pooled variance that we got up here, that 0.80, that's what's going to go into the top of this equation. And in the bottom, we're going to use the sample size for that first group, which was 6. So we divide these out, it gives us 0.13. For Y and its contribution here, when it comes to the standard error, we have again the pooled variance, which is the same number, that 0.8, and then we divide that by the sample size for the second group, which is 6. Gives us another 0.13. We then add those together. So this number and this one, 0.13, plus 0.13 gives us 0.26. So that is our squared estimate of the standard error of the comparison distribution. Now, this is still squared, so we need to convert it into an actual standard error standard error form. So we take that squared version up here, this 0.26, and we take the square root, and this allows us to turn this back into a standard error essentially for the estimate. So again, just putting it in terms of what we've done before, when we have the variance, in order to get the standard deviation, we take the square root. Here we have a squared value, and we have to take the square root in order to get that variability estimate of the comparison distribution. Now, step 4, determine the critical values or cutoffs. So, of course, we have to figure out what alpha would be, and we typically put it at 0.05, so a 5% chance of making a type 1 error. The next piece that's important is whether or not it's a one-tail or two-tail test. And earlier, well, during class actually, we determined it was a two-tail test. And we also need the total degrees of freedom in order to figure out what row we need to be on that table in order to figure out what those cutoffs are. So total degrees of freedom was degrees of freedom for the first group plus degrees of freedom for the second group, which gives us 5 plus 5, or 10. Okay, so if we go to the table and we look at degrees of freedom for 10. That gets us on the correct row. It's a two-tailed test that puts us in the second set of columns that deal with two-tailed tests, and the alpha or P level, which is what the book likes to call it, of 0.05, then gives us the exact values that we need for our cutoffs. So because it's a two-tailed test, we have a positive 2.228 over here, we have a negative 2.228 over here. And I've shaded in these regions which reflect the reject the null area. So if our calculated t-test statistic happens to be out in one of these shaded areas, it's out past the cutoff, and we would be able to reject the null. Alright, moment of truth. We calculate that t-test statistic here. And if you recall, one of the things about this formula is if our comparison distribution for mu sub x minus mu sub y is 0, so no difference between the population means, that 0 basically sort of drops out of the equation, leaving us with the mean for the first group minus the mean from the second group divided by that standard error estimate. So that basically gives us that 12.55 that we calculated, the 9.5, which is the mean for the second group, and that standard error estimate of 0.51. Plug those in up here. It gives us a t-test statistic value of 5.98. So this is what our sample data are telling us. Now, is it significant? Step number 6 in order to decide whether or not to reject or fail to reject the null. Well, I've put in here the cutoffs and shaded in the regions in the tail that would indicate the reject the null area. And then I had to extend the axis a bit because our t-test statistic was almost 6. So I've marked on here at almost the value of 6, the 5.98. So, decision being, do we reject the null? Well, yeah, it is way, way different than that cutoff. It's way beyond it. So, in terms of what we can conclude here, essentially, the individuals who got that post-hypnotic suggestion had statistically significant faster reaction times on average for the Stroop task compared to those who did not. And I'm in this statement sort of giving a direction here because I know what the means are. And the mean for the group that got the post-hypnotic suggestion was 9.5. The group that did not get the post-hypnotic suggestion had an average reaction time of 12.55, which is longer, which means they were slower. So, hence the statement here for a conclusion in terms of what happened with the hypothesis testing. Now, again, we have those additional statistics that we should be reporting. First one being the confidence interval, which in the case of the independent samples t-test, what is at the center of our confidence interval is actually going to be the difference between the two group means. Okay, so it's not going to be one or the other mean of groups. It's the difference between the two. So, again, first thing we do, sketch a distribution. We sort of mark off the size of this confidence interval, which we're going to go with the 95% to complement our hypothesis testing. And because it is a sort of by tradition, the size of the confidence interval it's typically reported. So I've got that marked off. That 95% is centered on the distribution, and in order to figure out what those mean differences would be for the lower bound and the upper bound, we need to go back to that table, get the statistics, the t-values that go along with those locations, which again, we had 10 degrees of freedom total, two-tailed test, because confidence interval is always going to have tails on both sides. And those cutoffs being minus 2.228 and positive 2.228. Now, the other pieces of information that we need in order to use the formula and get the lower bound and the upper bound are the mean for the first group, mean for the second group, and we need this estimate of the standard error. Okay? So, lower bound, we plug those values in. And of course, the difference between the formulas for the lower bound versus the upper bound of this confidence interval is that negative versus positive t value. So we have the negative one here for the lower end, and we have the positive version up here. For the lower bound, it gives us 1.91. For the upper bound, it gives us 4.19. Now, in terms of checking it, essentially, you want to make sure that the difference between your means is exactly between 1.91 and 4.19. So those distances should be equal. As far as reporting this in APA style, we have the percent interval that we are using, which is 95%. We have the lower bound of 1.91 and the upper bound of 4.19. Okay, effect size, because that's the other statistic that we should include with the results of hypothesis testing. So, Cohen's d. Again, we have two groups involved here with t-test. This is our effect size measure. So that formula has the difference between the means of our groups, subtract the mean of the comparison distribution, and then divide by the standard deviation of the pooled estimate that we got. So, as far as getting this number, this S pooled, we have to take the variance, the pooled variance, S squared pooled, and take the square root. So that was 0.8. Take the square root of that, it's 0.89. So essentially the standard deviation version of the variance is 0.89. We plug that in here. The difference as far as the comparison distribution goes, its mean is 0. So we end up with 3.05 divided by 0.89, or Cohen's d of 3.43. So, is that small, medium, or large? Well, if you recall, small is 0.2 for Cohen's d, the medium or moderate is 0.5, large is 0.8, and we have a Cohen's d of 3.43. So that is a fairly large effect size. Okay, so that essentially is the run-through for the worksheet that deals with doing an independent samples t-test in hypothesis testing.